Thank you very much for your kind words, Uli. And I wish to thank, first of all, you and Cesar and all the organizers for this invitation. That was, for me, a bit unexpected. So when I asked to myself why this invitation, I went to the homepage of this conference, and I read this sentence. So not many experimental probes can be employed to inspect the nature of polarons in material, in particular EPR. So this probably is the reason why in our group we have been working with EPR for several years, and although our research is not really devoted to study, I must say, the polaron phenomena, you are interested to the surface chemistry and photochemistry of transition metal oxide, in particular of photoactive oxide, semiconducting oxide. And for the reason we meet from time to time the problem of polaron. So I will try to tell you something coming and deriving from our experience. So this is a summary of this talk. I will speak mainly about titanium dioxide, but not only. Our materials, I have to say, are polycrystalline materials. It is better to be really rigorous to do EPR on single crystal, but this is not always possible, because there are real systems like those employed in photochemistry or in photovoltaic application that are polycrystalline systems, so you have to deal also with this real system. Really short introduction to EPR with no technicalities, then a part on all polarons in this, titanium, zirconium, and hafnium dioxide. Then the major part of my talk will be devoted to electron polarons in titanium dioxide materials. EPR is a magnetic resonance technique, and the formalism that through this technique is the spin Hamiltonian, and the main elements of the spin Hamiltonian are governed by metrics that are tensor. The G tensor and the A tensor are the more important for what I'm going to say today. G depends on the symmetry of the electronic ground state and from orbital admixture and contribution of the orbital momentum. The A is the hyperfine matrix. It's called hyperfine matrix, and determines the interaction between the electron spin and the nuclear spin that are in the surrounding. Okay, these are expressed, in particular, this is expressed in terms of two different contributions: the Fermi contact term related to s orbital, and the dipolar terms that holds for p and d orbitals. There are two kinds of approach in EPR. The classic one is the so-called CW, continuous wave EPR. You have simply a magnetic field that sweeps a certain region of magnetic field, and the sample is irradiated by a microwave. And when there is resonance, when resonance occurs, you record a spectrum. Modern techniques are, on the contrary, based on pulsed EPR. There is a sequence of pulses. I cannot enter in the technicality because there are many types of application. The main information that, or the main message we can keep in mind is that in this way you explore a wider region of your sample around the paramagnetic sample, because you become able to detect much weaker interaction, in particular much weaker hyperfine coupling. Okay, so I want to start with an old case in which, since here there is a problem that is interesting to this audience, and is the nature of the wave function associated to the polaron, and the problem of localization and delocalization. There is a case in which we were so lucky to directly measure the localization of a polaron. In the case of magnesium oxide is an insulator, so it's not a semiconducting oxide, 8 eV of band gap, but if you irradiate with a suitable frequency, you can also in this case separate and create an all polaron and an electron polaron, or no, something similar to an electron polaron. I cannot enter in this detail, but this is here is the signature of the the whole polaron, so the whole is stabilized in a particular place of our system. If you increase the power, you can get rid of the previous signal of this one. I don't want to discuss this. I did this in the past several times. And to observe the simple and very, very simple axial signal of this polaron. The symmetry of the signal tells you that there is the tensor is axial, and you have to find, since this is a surface signal, there are many elements, reactivity, etc., that tell you that it's a surface signal, so you have to find this whole polaron stabilized more or less here, I'm pretty sure, at this vertex of the crystal, where there is a ternary axis that explain such kind of spectrum. The G value is derived with a perturbation approach. There is a deviation for the free electron value that is due to admixture of orbital contribution. But this is not the important point in this moment, but the fact that we did another kind of experiment and we used water containing oxygen-17 because oxygen-17 has a nuclear spin, and so we can have more information if you have nuclear spin in the system, and normal oxygen-16 has 0 in terms of nuclear spin. And so we incorporated at the surface using water oxygen-17, and the same experiment produced another spectrum with an exciting information that is the hyperfine due to oxygen-17. From this value of hyperfine separation, you can go back to the contribution of the various orbitals to this, and what you find is that the spin density on the center is about 83%, and is essentially based on a contribution of a 2p orbital, dipolar contribution. The S contribution is practically negligible, is some spin polarization is something that is not important to compute, and this was published in the past. Just to see one case in which we were lucky to determine anything. As it has been told yesterday and during this conference, one of the possibilities to generate polaron pairs is irradiation. This is what it occurs, and as observed by EPR in the case of titanium dioxide, this is anaphase, irradiated with UV light, and once again, we are lucky to have, since EPR normally is very difficult in EPR to have resolved that situation. It's not an MR, unfortunately for us. Okay, but here is the trace of the whole polaron, and here is the trace that I will discuss in the following of the electron polaron. So, what can we do about the whole polaron in TiO2? It has been said something yesterday by Cristiana Di Valentin. We have really seen that the polaron stabilization is favored by defects. Everybody in this audience knows that. But one of the possible defects is the surface of the system. In particular, if the surface is hydrated, we have measured with a technique called END, or electronuclear double resonance, the interaction of the unpaired electron here on oxygen with the water that stays, the physisorbate water that stays around this site is with some nest of this type, okay? We just can say something about the distances between the unpaired electron and the proton of the water, and is 0.32 nanometers, and so this is compatible with a physisorbate layer. And this increased the number of all that are stabilized, and this can be interesting for people working in photochemistry and photocatalysis. This separation is not just for titanium dioxide. We have recorded this electron-hole separation and charge carrier stabilization in a number of oxides. For instance, this is zirconium dioxide. This is zirconium titanate. This is zinc oxide. As you can see, the whole is stabilized more or less in the same way. There are differences because depend on the symmetry, but are in the same region. Quite different is what it happens for the electron. There are very asymmetric and broad signal, or very simple signal, like in the case of zinc oxide. Now I would like to anticipate something that it will be useful in the following. And so there is another way to generate polarons, that is to introduce a single polaron in a system by doping. and this is a typical question of solid-state chemistry, so I will give you some information because it's a tricky problem. If in a semiconducting system you introduce an extra electron or an extra hole using a suitable chemical doping, you have two possible reactions, okay? Let's imagine to work on this kind of system, so titanium dioxide, zirconium dioxide, and you can put aliovalent means to put an element with a different charge, and so you can put aluminium, one less, or niobium, one more. And the response of the system is not granted. There are two possible responses that are determined by thermodynamics. In the sense that you can have the formation of vacancies. Here is an oxygen vacancy when you have aluminium, or a metal, a cation vacancy in the case of niobium. But you can also have directly the stabilization of a hole in the first case, or an extra electron in the second one. What I want to discuss today now, initially, is the case of aluminium, okay, and so we skip the niobium, and the case of aluminium doped titanium dioxide is such that the solution that the system prefers is this one. So we have aluminium in the system, in titanium dioxide, with some oxygen vacancy. Why I can say that? Because I don't see any hole. And the hole in this system are clearly visible because if we irradiate the system, okay, we can observe directly an hole, and the hole, as it is known to the people dealing with polarons, is strongly attracted by the defect. And so the hole stabilizes close to the aluminium. And this is visible by EPR because in normal titanium dioxide, fully dehydrated, you have such a spectrum. And in the case of the presence of aluminium, there is this beautiful hyperfine structure that derives from the nucleus of aluminium that has a nucleus being 5-half. And so there are 6 lines on each component of the tensor. So 6 lines here, 6 here, and 6 here. So this, okay, this all is interacting with aluminium. Now we have to do better and to do computation. And so this is our experimental tensor depicting this hyperfine interaction with a very tiny spin density, less than 1% on aluminium, very tiny. And these are the results of the computation that derive from a long-standing cooperation with the group of Gianfranco Pacchioni and Cristiana Di Valentin in Milano. There are two possible solutions. The better one is this, the best one is this. There is a very good simulation in particular of the Fermi contact terms. So we have a good computation of the system, and we can say something more. But we can also say something more about the other oxide. And for the other oxide, the situation is the same. We have this beautiful series of spectra obtained with aluminium-doped titania, zirconia, and hafnia. And in all cases, the G is different because there are different nuclei in the system, but you have always this series of 666 lines that allows you to measure the interaction, not, unfortunately, on the oxygen side, because it is oxygen 16 and not 17, but on the nearby aluminium. And this is a very tiny, tiny interaction that means that, once again, we have a strong localization of the hole on such an oxygen ion. And, well, now this is indirect, but since the hyperfine is very correctly simulated by DFT calculation, I can trust a little bit more on the data that are structural data derived by calculation. So this is the picture deriving from DFT of the distances in the system, so of the real polaronic distortion that is not a direct measure, I want to be honest, but is something that we trust, and we have some confidence in this because it derives from a fitting of the experimental spectrum with the DFT data. And so once again, in this case, there is a strong presence, a strong spin density on an oxygen ion on a p orbital in this case, okay? Well, this is the first take-home messages. Photo-generated polaron hole are observed in all this system. The APR described the interaction between the oxygen and the aluminium ion nearby, unless if you have oxygen 17 in the system, as I've shown. The delicate hyperfine parameters are well reproduced by FT calculation, and this indirectly validates the description of the polaronic distortion, this, in my opinion. So now I have to tell that I borrowed from the group of Chris van der Walle this beautiful image. And so between these two possible alternatives, okay, we are in this case looking to all the examples we have seen of polarons in oxide are of this type, so strong localization of the electron density on oxygen. So second part of this talk, titanium dioxide and the problem of electron. As I have shown previously, okay, you can irradiate a system and obtain electron and holes. Up to now we have considered the hole, but there are other systems, okay, that are reductive methods of annealing, and to reduce the system, these are reducible oxide, and you produce extra electron in the system, but also oxygen vacancy that perturb the system. Surprisingly, there are also oxidative methods. You can prepare titanium dioxide oxidizing a low valence compound, and also in this case you can obtain imperfect things, a non-stoichiometric oxide. Titanium dioxide is a world, is a continent. There are so many titanium dioxide. You can do the X-ray diffraction and obtain anatase in 10 cases, and the 10 objects are different. One is white, the other is black, the other is blue. It's a world, okay? So there is not one titanium dioxide. And then there is this interesting method that is the Valence alteration that I described before, that allows you to introduce one extra electron, in this case because you are talking about excess electron, using either a cation like niobium or an anion like fluorine. So I have to say that in all three cases, typical spectra of titanium 3+ are observed by EPR. So in some way, the excess electron interact with titanium and produce the titanium for ions. So the spectroscopy is not so complex because titanium 3+ is a 3D has a 3D1 configuration, and so is a one-half system. Otherwise, if there are 2 or 3 or 4 electrons, unpaired electrons in the system, you can do EPR, but it's much more difficult. So I'm pleased to discuss such a case because it's less complicated. The G value depends on the symmetry on the environment and on the energy of the splitting separation that can be very different in various cases. So these are, I just discussed not the tetrahedral case, it's not our case, but the octahedral case with the trigonal distortion in the sense of compression or elongation or trigonal distortion. This is perfectly ruled by the EPR theory, so there are no problems. Now we have to see what it happens, and so this is again the separation by photonic interaction, and we have to consider this signal of titanium dioxide. Keep in mind, please, that I call this titanium 3+1 because there is another titanium 3+ that is here. I can show it better, okay? You can see that is something that EPR people doesn't like because the signal is broad as is featureless, but it represents the majority of the electrons in the system because the intensity of the number of spin in the system is proportional to the line width and to the square of the line width. So it means that we have few electrons of type 1 and many electrons of type 2. I am also interested to show you where the polarons go, that this is interesting in a real system, okay? And this is an axial system, very nice for doing spectroscopy, but this is a broad one and we have to understand this. The same type of same type of signal appear when you reduce by annealing a system. At the beginning, there is no EPR, the S prepared has no excess electron, and then you start to reduce and the signal 1 appears. But very soon, the broad signal prevail, and at the end of the story is the second signal, titanium 3+2 in blue in my codex, okay, that prevails. Probably you all know, but if not, what is the reaction? The reaction is the elimination of oxygen by annealing. Oxygen create an oxygen vacancy when it goes out of the system, and the 2 electrons are stabilized around, okay? There is a lot of people today that believes that there are electrons in this vacancy and talk about F-center in titanium dioxide. I have never seen in all my life a true fingerprint of an F-center in titanium dioxide, because the electron likes the d electron of titanium, and it's there that it goes. Then, Okay, alteration, third case, alteration of the valence with niobium or with fluorine, and it's very nice to see that the result is the same. There is no difference in the spectra of titanium dioxide containing fluorine or containing niobium or containing both of them. Always there is this first signal, so titanium 1 and not the other one. So in this case we are lucky because we skip the second broad signal and we can concentrate ourselves on this kind of signal that is axial. It is actually normal EPR. If you go at higher field, we did an experiment at higher frequency, so 95 gigahertz, surprisingly, this signal is still the same, is axial, and this sends a message on the symmetry that we didn't understand at the beginning. We quite a long time to understand that it was a problem. It was telling us, sending us a message. Anyway, let's go to see. So titanium. So I will focus later on this kind of signal titanium 1, titanium 3+1. There are two questions now. So where are these two kind of species located in the nanocrystal? Because you know that there is one crystallographic position in a perfect crystal of titanium dioxide. And what is the nature of the excess electron wave function in this titanium 3+ center? And once again, the answer arrived using oxygen 17. Otherwise, you cannot say nothing more. Okay, oxygen 17, in this case, we used two different approaches. The first one is to enrich the surface, like in the case of magnesium oxide that I showed at the beginning, to enrich the surface with oxygen 17, and this is simple. You anneal, you create vacancy mainly at the surface, and you restore the oxygen using gaseous oxygen 17. So this is quite affordable. The second method to enrich all the system is much more expensive, I have to say, because water containing oxygen 17 is quite expensive, it's highly expensive, okay? But if you prepare with some hydrolysis method, okay, that are classical method to prepare anatase or rutile, you can obtain a sample enriched in all the bulk by oxygen 17. And this allows us to explain what we are observing. In this case, we use the technique that is electron spin echo envelope modulation, no technicality. The spectrum is the one you have seen in the form of derivative. Now this is the integral form, but it's the same. This is species 1 narrow, and this is the species 2 broad and featureless. It's absolutely the same. But what you observe when you point your field here or your field here is there is a different modulation of oxygen. Here there is the trace of oxygen 17. If you do the Fourier transform of this, you obtain the Larmor frequency of oxygen 17. So this species 2 is in interaction with oxygen 17. So it is at the surface, because we haven't reached the surface only. In the other case, there is some trace of far away oxygen 17, and so the narrow species is in the bulk and far away from the surface, not interacting directly with oxygen 17. So this is the first answer, okay, is the species 1 is narrow and well-defined and no echo modulation, so it's a bulk species. And if it is a bulk species, much probably, I will show that, is the regular site of titanium anatase, of titanium dioxide anatase. The second species must be at the surface because of this modulation, and so the model we derive is that there are few sites in the middle of and far away from the surface that are titanium 1, and a high number of sites that are at the surface close to the vacancy, and this explains also the heterogeneity of the system. Our surfaces are complex, so we are not so lucky to work on single crystal surfaces, so there are different phases, defects, vacancy, and so this explains also the featureless nature of our signal. So we have answered to the first question. And this is okay, more or less what I have in mind in terms of model, okay? Titanium 3+, blue at the surface, the red one in the bulk, okay? Now, electron localization versus delocalization. Okay, there is an open question. This is what is reported for the symmetry of titanium in anatase, and as you can see,
is not quite a regular system. It's not just a simply distorted octaedron, it's highly distorted. And so why we have an axial signal in this case? There is something that doesn't match, and we didn't understand this at the beginning. So is this axial signal compatible with the bulk side? Or unless if you have that you trap an electron, you become a polaron, and you suddenly become very symmetric, that is quite improbable, there is something that must be explained. And so we try to explain by comparison with the case of anatase, with the case of rutile. Rutile is much more symmetric, it's less asymmetric than the symmetry of titanium ion with respect of anatase. Nevertheless, we have a rhombic system with 3 components and not axial system like in this case. There is a series of work on single crystal on rutile that have been performed by the group of Larry Halliburton in the United States, and this is one of that. And there are some small difference in the G values that you record on powders, but this is not, must not discuss it now, otherwise it's too long. In any case, we are in the area of polarons in rutile. You see that in spite of this small difference, the two spectra are really to be really different one from the other. In rutile, there are 2 important sites. The first one is due to a bulk site, and the second one is due to an interstitial site that is a defect. We have measured this, it was present in the previous slide, but we have assigned it on the basis on a single crystal study that really plays, and this has been done in the past by Ono and Dasiguti, really plays the coordinates of this signal in an interstitial site. So we have at least 3 distinct signal to explain in terms of localization or delocalization. One in the rutile, the second one in the rutile, and the third in anatase. We have to rely, once again, on pulsed EPR and on the, now, in this case, on the oxygen-enriched system in the bulk, so the second type of enrichment, okay? Well, the first problem is that the main site of rutile is not possible, it has been not possible to measure the spin echo for this one. It's a question of relaxation time. It's not our fault, it's the fault of the system. And so we have to rely on 2 systems only, the anatase system with the strange, now I can say axial system, and the interstitial site of rutile that can be increased in terms of, with a simple trick in the preparation, increase in terms of amount. In this case, we can record the spectra. And if you do the normal EPR, continuous wave EPR, you see that there is absolutely no difference between the 2 spectra. So it seems pretty useless to put oxygen-17 in the system. But if you do pulsed EPR, there is a difference because there are very tiny interactions. And so to check this, we started from, to train ourselves on a well-defined case. And the well-defined case is not a solid, is a molecule, okay? And the molecule is the aqua titanium in solution. You dilute this enormously in solution, so you have a molecule, no problem, localization, delocalization. The electron is there in the orbital of titanium, and is also all the calculations that are very simple in this case because it is a model tell you that it's very localized here. So what is the interaction with water in this case, or with the oxygen of the water that mimic a little bit our system is recorded here, and you have to keep in mind this figure is about 8 megahertz. It's extremely tiny, it's really nothing, okay? And this is a true localized system. So now look at what we had in the case of our 2 system. This is water. This is a rutile interstitial site, similar thing. You have to see this quadrant, and this separation is important. 7.8, 8.2 is the same, so strongly localized system in rutile. And this is an interstitial site. I guess, I think, but I'm not sure because I can measure this, that the normal site in rutile, the lattice site, main site, is probably the same, but there is no echo, I cannot do that. But the amazing result is here. In the case of anatase, our strange regular spectrum, axial spectrum, there is no interaction visible at all. What we see in this quadrant is something that is probably of the order of 2 megahertz, so much less of the case of a strong localization. Does this mean an even higher localization? No, this probably means delocalization. in some domain that has an axial nature, an axial symmetry, and that explains this, this strange shape of the spectrum. And so this is what we've done. I'm finishing. When we wrote this, okay, we have tried to describe this, and we have also seen what it has been done in the literature, okay? And in this case, there is a beautiful review paper by Christian, Annabelle, and Gianfranco that tell us that in this case, theory is not able to really decide between a localization solution and a delocalized solution from this case of electron trapped in the bulk of an lattice. But on this basis, since the energy of these two systems is nearly the same, on the basis of our result, we selected this solution and we published these results time ago. Okay, so we imagine that this symmetry is due to the delocalization in some domain with an axial symmetry. To our satisfaction, there is a paper appeared in the literature practically in the same time by Uli, Cesare, Franchine, Chris van der Waal, George Kresse, so it's a paper with many important persons, okay, where by completely different approaches, scanning tunneling microscopy, they conclude that in rutile, excess electron can localize at any lattice titanium atom forming a small polaron. In contrast, electroionatase prefer a free carrier state. So we are telling and sending the same message. We are telling and sending the same message. Okay, I have just 4 minutes, but there is a final feature that I want to show because it's really interesting, and we were not able to tell to the community this message probably in a more clear way. Let's go back again for a minute to the N-type TiO2. So enriched with fluorine or niobium is the same system. There is something that makes a strong difference between pristine anatase and this doped system. And this that if you have doping in the system, initial doping in the system, any evolution of the system is conditioned by this doping. Look to the annealing in vacuum. This is bare anatase. You have already seen this spectrum, okay? Initially, the species 1, and then the big, enormous species 2. It's not the case for the doped titanium, both with niobium and fluorine. Species 1, always species 1. This grows because there is magnetic interaction, but it's always the same species, and there is no this distribution at the surface. So the electron remains in the bulk. Even if you irradiate, it's the same. Here is the result of irradiation of pristine TiO2. I have already seen this spectrum. Here is the niobium enriched. So there is an initial spectrum because niobium is in the system, but all the other trapped electrons have the same feature of the initial one. And so there is this big difference. If you inject hydrogen atom, it's not difficult to do that, okay? You have the 2 signals with normal titanium and 1 signal only. Look, this is beautiful because it's the same signal that grows in intensity. So the message is that in this case, you get a uniform distribution of the free carrier state. And this is not unimportant for people working in application in photovoltaic, etc. So this is the final slide, okay? And so 2 types of messages in pristine or bare titanium dioxide. You go by reduction or by irradiation to this kind of situation, few polarons in the bulk, okay, and are delocalized polaron, and many things at the surface. But if you start from this situation of enriched material, you obtain a much more uniform material. And there is another proof of this, and this is the optical absorption. The optical absorption is dramatically different in the 2 cases. Dramatically different because here is this case. There is a broad absorption, but the maximum is here, 0.8 electron volt. And in this case here, the maximum is in the infrared. So we are talking about very different state, narrow state, etc. So I have finished my talk. I skipped the last two things related to states of interaction of polarons, magnetic interaction of polarons creating high spin states is less important today. And so the second take-home message, okay, oxygen 17 investigation allow to discriminate between surface and bulk. Two opposite cases of electron trapping have been described, localized at mole polaron in rutile, and delocalized electron density bulk site of anatase. So in this case, we have both, okay? Again, borrowing from van der Walle this beautiful picture. And the N-type doped material behave differently from pristine titanium oxide when an excess of electrons is generated. So let me thank finally the people of my group, that these are the permanent person. Let me acknowledge the long-standing cooperation with Gianfranco and Cristiana. This is our group in a recent, so we were in the Lange region, where the rainbow was booked for the special occasion, and I thank you very much for your attention today.
Thank you very much, Elio, for this nice talk. Any questions? Yes, please. We should use the microphone. So don't mind.
So I'm curious if these type 1 and type 2 Ti3+, imagine if you have a particle that gets smaller and smaller, it's harder to distinguish between the two as you go to a smaller.
If the particle is, well, the particles we are considering are really nanocrystal. The size is about 40, 50 nanometers of diameter, so are really small. And there is this accumulation at the surface that creates this broad nature. I am sure that there is a dependence of the size. If you grow crystal, you obtain a decrease of we have observed this in rutile, I have to say. With using a rutile with relatively big crystal, the surface practically disappears. So this is a phenomenon that is present, especially in highly divided material.
So if you go to like a smaller nanoparticle, what do you expect to see in your signal?
In the smaller nanoparticle, well, it should be the same. I mean, maybe that the width of the signal increase, so we have even more broader signals.
Did I understand correctly that you said that you have a delocalized electron, but at the same time you have extra symmetry of the state?
This is a tricky question. I have really no answer. I mean, our idea and our position has been a suggestion, a message to the audience and to the expert. The problem is that, and it's what we didn't understand at the beginning, such an axial signal that we observe must be typical of a very regular site. And we can observe this in some molecules that are intrinsically much more regular. It is strange to have such an axial symmetric signal for something like titanium in anatase that is highly distorted. It's for this reason that coupling this with the result of the hyperfine clapping in oxygen allows us to propose this delocalization. But frankly, I want to be honest, it's not a direct observation. It's an indirect deduction, okay? And that is corroborated by what Uli did here in Vienna.
Thank you.
For the oxygen vacancies in rutile, from most of the calculations, it is all, I think the ground state is always like a singlet, but apparently EPR, what you detect is unpaired electrons. Can you comment on this a bit?
Okay, there are several possible issues. So depending on the condition of irradiation, the nature, etc., you can have both S equal 1/2, so one single polaron titanium. That means, if you want, an excited oxygen vacancy, but also, and Ali Barton did this observation, triplet state with two titanium triplets close to a vacancy. Is a state that is rather unstable, is observed at 15 K, and at 20 K is already excited. So we have to keep in mind that many of observation depends on the temperature, and so the true system, maybe the ideal system can be described close to 0 Kelvin, but if you rise the temperature, many different things can occur. So certainly there are, but what it is sure, and I think that calculation done by Cristiana and Annabella can confirm, is that if you put out an oxygen, you create an oxygen vacancy, the electron tend to ionize, it's called ionize from the vacancy and being stabilized on titanium ion. In some case, close to the vacancy, triplet, or one far away and the other here, singlet, or the two far away, we have seen where. Okay, this is more or less my idea.
Then just a quick follow-up. So is it then possible to have a low temperature measurement for EPR?
So the main part of EPR you have seen are recorded at 77 K, at liquid nitrogen, the continuous wave. The pulsed EPR, this with oxygen 17 delocalization, at helium, liquid helium, so let's say in between 5 and 10 K, okay? So we are, the delocalized state is a state observed at this temperature. At room temperature, these are probably ionized in the conduction band or